So if I have the square root of 20, I can factor out the square root of a perfect square. Okay, so that's what's taking place here. They're factoring out the square root of 4 times the square root of 5. Okay, because 4 times 5 is 20. And we know the square root of 4 is 2. I can't take the square root of 5, so that would be 2 times the square root of 5. Okay? Using this method for the square root of 27, I could factor out the perfect square of 9. And so square root of 9 times square root of 3 would be square root of 27. And I can take the square root of 9 and get a whole number 3. So 3 square root of 3. And they go on with this method. Square root of 48 equals the square root of 16 times 3. 16 is a perfect square, so we can take the square root of 16. That's 4 square root of 3. Okay, on number 4, I've got the square root of 45. 45 is equal to 9 times 5. I can take the square root of 9. That gives me 3. And so it's 3 square root of 5. Square root of 12, I can factor out the perfect square of 4. So square root of 4 times square root of 3. Square root of 4 is 2. So I have 2 times the square root of 3. So on number 6 with 50, what I would do is I'd take the square root of 25 times the square root of 2. And the square root of 25 we know is 5. And we've got the square root of 2 that carries over because I can't take the square root of 2. Okay, on 7, now this is what happens when we have an odd exponent. I really want you to pay attention to this. If I have a to the 5th, that is equal to the square root of a to the 4th times square root of a. In other words, I took 1 away from my exponent and put it in its own exponent by itself. That gave me an even value for my exponent. And because it's an even value, then I can divide it by 2. So square root of a to the 4th would be 4 divided by 2, so a to the 2nd times the square root of a. And I can't take the square root of a because it wouldn't come out evenly. Okay, so for x to the 9th, 1 from 9 is 8, so this is going to be square root of x to the 8th times the square root of x. Half of 8 is 4, so this would be x to the 4th times the square root of x. And then on number 9, I've got the square root of x to the 3rd. Take 1 away from that, that's x squared times the square root of x, which would be x square root of x. All right, now, that gets you through these sums. However, there's something that I have an issue with, and I'll tell you what it is, okay? For years, whenever I was doing square roots, I'd always kind of second guess myself, and I practiced it, and I practiced it a lot. But I know that for you guys, this is going to seem pretty tough because, say for instance, the square root of 18, there's a number of ways I could divide 18 up. So I want to show you guys this method, and it's called the 2-column method. And I find it really useful, and it helps students out a lot, okay? And I think if you do this, you'll do better on your quizzes and tests. So on number 18, or number 1, I'm sorry, that should be number 1 from this bottom set of questions on the worksheet. I've got the square root of 18. Okay, so I'm going to practice the 2-column method. And in that, I'm going to put 18 on the right-hand side. And now, when we're working with prime numbers, the prime numbers are only divisible by 1 in themselves. So let's list those up here at the top. The lowest prime is the only even prime, which is 2. 2 is only divisible by 1 in itself. The next one is 3. 3 is only divisible by 1 in itself. What would be the next prime number? Next number only divisible by 1 in itself.
5.
Okay? And after 5, we have 7. And after 7, 8's divisible by 2 and 4. It doesn't work. 9's divisible by 3. That doesn't work. 11 is prime. Yeah. And after 11?
13.
Okay. And after 13?
17.
And then after 17?
19. No.
Yeah.
What? For real?
Yep, it is. And so these prime numbers are what I'm going to use to factor. So I'm looking at the 18 and I'm saying, okay, what is the lowest prime number that will divide evenly into 18? And that is 2. 2 goes into 18 how many times?
9.
Okay, so I'm going to put the 9 down here because 18 divided by 2 was 9. Okay, now what's the lowest prime that will go into 9 evenly?
3.
And how many times does it go in?
3.
Okay, now at 3, I'm going to say something special to myself. I'm going to say Kayamishi. Okay? And Kayamishi means I will go no further. The story goes that when the Choctaw Native Americans were brought to eastern Oklahoma, they had traveled on the Trail of Tears for a number of miles across several states. And they got to eastern Oklahoma, and they got to this range of mountains, and the chief said, Kayamishi. And the Native Americans, they, all kind of sat down. Well, the soldiers that were guiding them, they looked kind of funny, and they looked up, and they saw these hills, and they said, oh, well, these must be the Kayamishi Mountains, because the chief is saying Kayamishi. What the chief was saying is, I will go no further. And he pointed to the mountains. He was like, I'm done. I'm done walking. I will go no further than the tops of these mountains. I'm finished traveling. And so that's what Kayamishi means in Choctaw. I will go no further. So if you see Kayamishi Mountains, it's that I will go no further mountains. Kayamishi Votek, again, named after the Kayamishi Mountains or that story, right? So, and the Choctaw people have made the area of eastern Oklahoma their home. You know, they're not going anywhere. They're staying there. Okay, so when I get to a prime number, that's why I say Kayamishi to myself. I am not going any farther because I've gotten to a prime in my list. Now, here's what I've got. I'm going to cross out everything that's not prime. And I've got a pair of 3s that I'm going to circle. Anything that I have a pair of. Now, to be a pair, they have to match. It's like a pair of shoes. They have to match. My daughter wouldn't wear a high heel shoe on the left foot and a tennis shoe on the right. That would not be a pair. It'd be kind of hard to walk too, right? But to be a pair, they have to match. So they have to be the same. So I've got a pair of 3s and I've got a 2 left over. Now anything that I have a pair of, I'm going to write outside the radical. Because we know 3 times 3 is 9, and the square root of 9 is 3. I've got a 2 left over, and it's going to go back under the radical. Okay, now, with my explanation, that took a lot of time. But using this method, it can really speed things up when you actually get into doing this. So, say for instance on number 2, I've got the square root of 125. Okay, so 125. It's not even, so it won't divide by 2. 3 goes into 12 4 times and into 5 once with 2 left over. 3 won't fit evenly. 5 goes into 125 25 times. And 5 goes into 25 5 times. 5's prime, so Kiamichi. I will go no further. I'm going to circle a pair of 5's. I have a 5 left over. Okay, so 5 times 5 is 25. Square root of 25 is 5. Square root of whatever was left over, which is the 5. Okay, number 3. Square root of 72. Okay, so 72 is even, so 2 goes into 72 36 times. 36 is even, so 2 goes into 36 18 times. 2 goes into 18 9 times. 9's odd, but 3 will go into 9 3 times. Okay? 3's prime, so I'm going to stop there. I'm going to cross out everything that is not prime. I've got a pair of 3's and a pair of 2's and 2 left over. So that would equal 3 times 2 times the square root of 2, which would be 6 square root of 2. Okay. Number 4, square root of 180. Okay, so 2 goes into 180 90 times. 2 goes into 90 45 times. 45 is odd, so I can't use 2. But 3 will go into 45 15 times. And 3 will go into 15 5 times. Cross out everything that's not prime. I've got a pair of 3's. I've got a pair of 2's. There's a 5 left over. So, it's going to be 2 times 3. And I've got the 5 that's left over that goes back under the radical. So my solution is 6 square root of 5. Okay, number 5, a cubed. Well, if I have the cube or the square root of a cubed, we know that's equal to the square root of a squared times the square root of a. Square root of a squared is a, so a square root of a. Okay, 6, same sort of thing. I've got the square root of b to the 7th, which would be square root of b to the 6th times the square root of b. That gives me b to the 3rd square root of b. Okay, let's skip over to number 8 now. Okay, 8 has all kinds of goodies in its bag. Okay, we've got the square root of 75 x to the 7th y to the 5th. Okay, so I'm going to have to handle each of these pieces separately and then bring them back together again in the end. So 75, well, let's see. 2 won't go into 75. 3 will go into 75 25 times. 5 will go into 25 5. Got a pair of 5's and 3 left over. So that gives me 5 square root of 3. Okay, for the square root of x to the 7th, that's equal to the square root of x to the 6th times the square root of x, which would be x cubed times the square root of x. So we'll bring that over here. And then I've got the square root of y to the 5th, which is the square root of y to the 4th, square root of y. That would be y squared times the square root of y. So, when I get done with all three parts, then I need to look at the stuff that's not under the radical. And I need to group it together. So I've got 5 times x to the 3rd times y to the 2nd. And then underneath the radical, all that stuff's going to go back together. So I've got a 3, I've got an x, and I've got a y. And that is our simplest form. So let's do another one like that. Let's look at 10. Okay, I've got the square root of 32, a to the 7th, b to the 4th. And that's going to be equal to, okay, so let's start with the 32. 2 goes into 32, 16. 2 goes into 16, 8. 2 goes into 8, 4. 2 goes into 4, 2. So I've got one pair of 2s, another pair of 2s. That's going to be equal to 2 times 2 times the square root of 2. Okay, the square root of a to the 7th is equal to the square root of a to the 6th times the square root of a, which would be a to the 3rd square root of a. And then for the square root of b to the 4th, well, that's going to just be b squared, right? Because we can divide that in half. Okay, so 2 times 2 is 4. A to the 3rd, b to the 2nd, times the square root of 2a.